Okay, let's unpack this. We are diving into a truly radical idea, one that sort of redefines how we experience the most fundamental dimension of our reality, time itself.
It really does.
For years, we've basically accepted this idea that perceiving time is like seeing or hearing. It's continuous, it's scalable.
Right. You can always have a little more light or a little more sound. The assumption was you can always have a little more time.
Exactly. But that's the traditional view, and our deep dive today is going to challenge it completely.
It is. We're focusing on some groundbreaking work, synthesized beautifully by David Gilden in The Psychology of Human Temporality, which proposes that our temporal experience is, well, it's not unbounded.
And Gilden's approach is just this remarkable synthesis. He pulls from music theory, experimental psychology, even theoretical physics.
Which makes sense given his background. He was an astrophysicist first.
Right, so he's bridging these huge conceptual gaps in a way that feels, I don't know, totally unique.
And the central, really bold claim is that the human mind does not perceive time as this infinite ribbon that you can just measure however you want.
Instead, there's a boundary.
A hard, fundamental, physical boundary. There is a moment, a threshold, where what he calls felt time literally just dissolves. It turns into something else. He calls it a phase transition.
A phase transition, like water turning into ice. It's not a gradual change.
Precisely. It's not getting fuzzier. It's becoming something fundamentally different.
And our mission in this deep dive is to explore how this critical limit, this now famous 2 ± 1 second boundary, dictates pretty much everything.
Everything from why a melody holds together to how we organize our short-span memory, and this is the most surprising part, how this limit is physically anchored to the size of our own body.
We're basically charting the edge of the known psychological map.
Exactly. We're finding where the dragons are.
Okay, so to really get how revolutionary this is, to impose this hard limit on time, we have to travel back a bit, back to where psychology itself kind of started.
To sensory psychophysics.
This was, post-1890. Where researchers were trying to find these objective mathematical laws for our subjective internal experience.
They were focused entirely on one thing: magnitude. Psychophysics asked a very simple question. How does the objective, measurable physical energy out there,
Like the brightness of a light.
or the frequency of a sound wave, how does that relate to our subjective internal experience of brightness or pitch?
It's all about finding the relationship between the outside world and the inside world.
It is. And because durations can be long or short, they have magnitude time just got swept into this paradigm along with everything else.
Light, sound, time, they're all what they call prosthetic continua, right?
Yes. Anything that can be graded continuously by size. If it had magnitude, psychophysics wanted to measure it and fit it into this grand unified system.
And the most iconic achievement of this whole field was, of course, Stephen's power law.
Right. This was the mathematical structure. It relates the objective stimulus intensity, let's call it I, to the perceived subjective magnitude, which is psi of I, using a simple exponent, alpha.
And this law was such a revelation because it showed that our perception isn't just a direct mirror of the world. Our mind is more like a distorting lens.
A distorting lens is a great way to put it, and the amount of distortion is revealed by that exponent, by alpha.
The examples here really make it clear. Let's take electric shock.
Okay.
If you just slightly increase the physical voltage, the pain you feel, it just skyrockets.
It accelerates wildly, yeah. A tiny bump in voltage feels like a massive leap in torture. The exponent for electric shock is incredibly high, something like 3.5.
As the system is designed to just scream S-to-P immediately.
Exactly. But then you have the opposite, like brightness.
Right. The experience there decelerates.
Yeah.
If you double the physical light intensity, your perceived brightness goes up by a much smaller amount.
It does. The exponent for brightness is low, around 0.33. And this is a crucial design feature. I mean, if our eyes perceived light linearly, stepping outside on a sunny day would just be blinding.
It would be a total sensory overload.
So the low exponent dampens the system, letting us operate across this huge range of light intensities.
So we have these highly accelerating experiences like shock and highly decelerating ones like brightness. But when they applied Stephen's law to time, they found something weird.
They found an exponent of alpha equals 1.1.
1.1, which is, for all intents and purposes, that's linear.
It's practically linear, yes. It suggests that when you perceive time, the mind doesn't apply much distortion at all. If the objective time doubles, the subjective feeling of that time almost exactly doubles.
So time was perceived veridically, accurately. And this was treated as proof that timing was just another continuous sensory experience.
Mm. And that finding really set timing theory in stone for decades. But the psychophysicists weren't just interested in the magnitude. They also had to deal with the error, the uncertainty in our judgment.
Right. Nobody's perfect. We don't say 30 seconds. We say 30 seconds-ish.
And that brings us to Weber's law.
Weber's law. This one feels like common sense, but it's so important. It just says that the uncertainty of your judgment, that ish factor, is proportional to the size of the thing you're judging.
Right. Think about distance. If I ask you to measure out a foot with your hands, your error might be an inch. But if I ask you to estimate 100 feet, your error is going to be way bigger, maybe 10 or 15 feet.
The uncertainty grows with the magnitude.
Exactly. And in the context of time, it means your error margin for judging a minute is much bigger than your error margin for judging a second.
And they study this a lot with animals, right? The peak interval procedure.
Heavily, with rats, pigeons. You train them to respond at a specific interval, say 15 seconds, to get a reward.
And if you plot their responses, you get this bell-shaped curve that peaks right at 15 seconds.
Yes, and the width of that curve, often called the full width at half maximum, or FWHM, that's your ish factor. That's the measure of their uncertainty.
And they found it confirmed Weber's law perfectly.
Perfectly. The uncertainty at 30 seconds was about double the uncertainty at 15. The error grew proportionally. So the system looks scalable, unbounded. Just keep counting the internal pulses.
And this is the whole beautiful picture that Gilden is rejecting, this idea of time being linear, scalable, with predictable error.
He says this picture is profoundly misleading because it's based on one huge, flawed assumption.
Which is?
That the experience of time is unbounded.
That's the phase transition argument. You can't just treat duration like light or shock and assume it goes on forever.
Exactly. He argues that beyond a few seconds, the subjective, felt experience of duration just stops. It ceases to exist. It's not that the judgment gets fuzzy. The very fabric of the experience changes.
So that nice linear Stevens law curve for duration is actually a lie.
It's a lie because the data only applies up to a certain point. Beyond that point, the perception itself collapses.
And Gilden visualizes this by just drawing a dragon on the map.
He replaces the nice linear curve with a massive hard boundary. A dragon at the 2-second mark. Here be dragons. Beyond this point, our direct perceptual system is in uncharted territory.
That's a huge conceptual shift. If we're not continuously sensing time as a magnitude, then what? What is happening?
To understand the boundary, we have to pivot. We have to move away from sensory psychophysics and its focus on magnitude and go towards Gestalt psychology.
Gestalt, which is all about relationships and organization.
Exactly. It's not about sensing the quantity of things, but how the mind actively creates the world through organization. The word itself means form or shape.
The core idea being that when elements come into relation with each other, they form a group, a whole, that's more than the sum of its parts.
Right. Give us the classic example.
Well, 3 dots.
The 3 dots? I show you 3 distinct physical dots on a screen. Physically, they're just 3 positions, but you don't see 3 dots.
You see a triangle. The triangle is the Gestalt. It's this new, unified thing that wasn't there in physical stimulus alone.
Your mind is actively organizing the world, not just passively receiving it. And a key part of this is that grouping isn't fuzzy.
Right. It's not like something can be half in a group and half out.
But it's what they called the rule of either. You're either in the group or you're not. Think of the duck-rabbit illusion. You see a duck or you see a rabbit. You don't see some weird duck-rabbit hybrid.
The mind picks one unified structure.
Which makes this limit so critical. If the Gestalt principle of relationship is how time enters the mind, we feel time because moments relate to each other, then that 2 plus or minus 1 second boundary must be the point where that relationship just snaps.
It's definitively severed.
Yes. The group dissolves, and that feeling of togetherness vanishes into mere succession. You no longer hear a melody.
You just hear a series of unrelated sounds. And that vanishing point is the boundary.
And the thing is, this theoretical leap from psychophysics to Gestalt, it's huge. But what makes Gilden's argument so powerful is that this phase transition, this dragon's edge, is tacitly confirmed everywhere you look.
In dozens of totally unrelated domains.
It's the consistency that's so stunning. This isn't just some artifact of one lab test. It shows up in how we design metronomes, in memory tests, in our most basic physical movements.
Let's start with music. Music is, at its heart, the art of structuring time into meaningful groups.
Right. We understand that a melody relies on preserving the ratio of time between the notes. If you speed up a song, it still sounds like the same song because the ratios are intact.
But that only holds up to a certain point when you slow it down, when you start expanding the time between the notes.
And there was a classic experiment on this. Warren and colleagues in 1991, they took familiar melodies like Happy Birthday and just progressively slowed them down.
And what happened?
The melody just dissolved. It didn't sound slow or strange. It just broke apart into what they called unrelated sound islands.
The Gestalt was lost.
Completely. And they pinpointed this dissolution threshold when the time between the notes reached a median of about 1.3 seconds.
1.3 seconds. That is incredibly precise. And it puts us right in the heart of that 2 plus or minus 1 second range.
The mind can no longer hold the beginning of the relationship, that first note, in active connection with the end, the second note.
It stops being music and just becomes temporal debris.
And you see the same thing with the feeling of rhythmic pulse, the tactus, that fundamental beat that makes you tap your foot.
That's also an emergent property, right? It's created by the group of beats.
Yes, and that pulse also dissolves at very slow tempos. A drummer can hold a beat down to a certain point, but if they go too slow, they're not creating a rhythm anymore. They're just hitting individual notes.
And we see confirmation that's not in a lab, but in in how metronomes are made.
The ethology of metronome manufacturers, it sounds funny, but it's true.
These are the devices musicians actually use, so they're designed for what's practically useful.
Right.
And they don't bother including tempos that are musically useless.
Right. So what's the slowest tempo they typically support?
It's usually 40 beats per minute, 40 BPM.
And if you do the math, the time between clicks, the interbeat interval for 40 BPM, is exactly 1.5 seconds.
So the entire world of music production, completely independent of psychology, has concluded that anything slower than 1.5 seconds is basically pointless.
The feeling of rhythmic pulse, the emergent Gestalt property, is just gone. The two beats are too far apart to be grouped as a rhythmic whole.
So across melody and rhythm, the limit consistently lands between 1.3 and 1.5 seconds.
But it's not just in sophisticated things like music. It's pervasive in what Gilden calls the low culture of laboratory life.
The unwritten rules that experimental psychologists use to design their studies. I love this part.
Because the scientists aren't measuring the limit, they're just assuming it exists because everyone knows it's true.
Okay, take memory studies, list learning.
Right. If you want to study false memory, you present a list of words. To make sure the words are heard as separate discrete items, as word islands, you have to put a pause between them.
You want to prevent the participant from grouping them into a chunk.
Exactly. You need succession, not relation. So what pause length do they universally choose to achieve this separation?
It has to be 1.5 seconds.
1.5 seconds. The implicit knowledge is that this is long enough to break the temporal grouping mechanism. If the mind could group things over, say, 10 seconds, this pause wouldn't work.
And you see this in reaction time experiments, too. Lexical decision tasks, where you have to judge if a string of letters is a word.
The goal there is to measure the processing time for one discrete cognitive event, one trial. So you have to make sure the trials are perceived as separate events.
You need a gap between the end of one trial and the start of the next, a temporal moat.
And that separation gap is typically 2 seconds.
2 seconds. And the inverse is also true, which is so telling. If you want to bridge two events, like a ready cue and the actual stimulus,
use a much shorter gap, often a 1-second fixation box.
So 1 second to encourage fusion, 2 seconds to guarantee separation. The tacit knowledge of this boundary is just baked into the methodology of the entire field.
It's fascinating, the unwritten rules of science reflecting this universal cognitive constant. But let's look beyond the lab. What about our physical lives?
How we choreograph our own existence.
Exactly. Margaret Schleidt and her colleagues analyzed the choreography of everyday human movement across different cultures. Things like stirring coffee, grooming, gestures, even just head nodding.
They were looking for the natural duration of these motion-defined groups.
These little packets of action that define a single meaningful movement. And their main finding was that these action units typically last for 2 to 3 seconds.
A universal constant in temporal segmentation.
So we unconsciously structure our own behavior to fit within that 2 plus or minus 1 second window. A single meaningful action has a beginning and an end that can be perceived in relation to each other.
And this brings us back to the psychologist who really explored this directly, Paul Fraisse.
Fraisse and his capacity of apprehension, he was asking, How much time can separate two events while they still feel like they belong together?
His examples were so tangible. How long can the gap be between tick and tock before they're not a pair anymore?
Or between bit and ter before they stop sounding like the word bitter and just become two random noises?
This is the subjective experience of that Gestalt boundary.
And his conclusion, through introspection and observation, was that the maximum interval for this fusion is consistently around 1.5 to 2 seconds.
It's just stunning. Across music, memory experiments, movement, introspection, we just keep converging on the same number.
The dragons are not moving. They are consistently placed at the same spot on the map. The phase transition from relation to succession is not just a theory. It's a universal, empirically verifiable limit of human experience.
So now we have to go from the what to the why.
What is the mechanism?
Okay, we know the boundary is 2 plus or minus 1 second. Now the critical step, what is the dynamic mechanism inside the mind that is enforcing this strict temporal boundary? It can't be a little stopwatch.
No, it has to be a physical process. And Gilden argues that the short-span memory that underlies this grouping is totally different from what we call short-term memory or working memory.
Not the kind that holds 7 plus or minus 2 digits.
No, this is a memory without containment. It's not about storing items in a buffer. It's rooted in the physical evolution of a dynamic system.
That sounds pretty abstract. How do we define that kind of memory?
Well, in physics, memory is simple. A system has memory if its current state is influenced by its past states. And for this, we're talking about priming.
Priming. Where a past experience temporarily changes your readiness to do something, a spike of activation or suppression, without you even having to consciously remember the first event.
Exactly. It's an ephemeral, highly physical dynamic in the nervous system. And crucially, we can measure the life history of this activation by taking delayed behavioral samples. We can see how long the influence lasts.
Okay, let's start with semantic priming, the classic Dr. Prime's nurse example.
Right. You see the word doctor, and it temporarily activates related concepts. So you recognize nurse faster than an unrelated word like, say, butter.
And researchers have tracked this effect over time.
They have. The activation peaks around 1 second after the prime. But the key is the decay time. The semantic influence typically decays back to baseline, back to 0 after about 3 seconds.
So after 3 seconds, the prime has no effect. Nurse is recognized just as slowly as butter. The temporary life of that idea is over.
And now consider the opposite, negative priming, an inhibitory effect.
This is where, if you have to actively suppress the word blue to name the color red D, you're then briefly inhibited from using the word blue.
Yes, and this lingering suppression also decays. And it was found to decay entirely, returning to 0 influence after about 2 seconds.
A bit faster, but still right there in that 2 to 3 second window.
And finally, you have motor or perceptual priming. The boost you get from seeing a shape you just responded to, that also has a half-life of just a couple of seconds.
So all these different forms of non-conscious, ephemeral, memory semantic, inhibitory, motor, they all share the same very short temporal lifespan.
It strongly suggests a singular underlying clock mechanism, and this mechanism has to follow a specific type of decay law.
Gilden argues it has to be an exponential law, not a power law.
And this distinction is critical for understanding why the limit is so absolute.
Why can't it be a power law? That's what's often used for long-term forgetting, right?
Right. A power law implies that the resistance to forgetting grows with the age of the memory. Older memories are harder to forget. It's like aging wine.
But activation isn't stored or aged like that. It's an energy state that's just dissipating.
Exactly. It's not being recalled from a shelf, it's just becoming less. So the appropriate physical law is the exponential one, where the rate of decay only depends on how much activation is present right now.
It doesn't care how old the activation is. It's like radioactive decay.
And that constant rate of decay is defined by one term, tau, or tau.
Tau. The time scale or the activation lifetime?
It is the natural unit of time for this system. After 1 tau interval has passed, the activation drops to about 37% of its starting value. It is the intrinsic clock constant that defines how fast this temporary mental state dissipates.
So tau is the throttle of the system. It sets the maximum possible duration for perceiving relatedness.
You can think of it like a valve. The valve opens when you see, say, the syllable bit. As time passes, the valve starts to close as the activation dissipates. We live in the now only for the duration until that valve closes.
And if that temporal horizon defined by tau is about 2 seconds, that gives us the mechanism for the Gestalt phase transition.
This is where it all comes together. The phase transition happens when the activation history overlap between two successive events is lost.
Back to bitter.
When event 1, bit, generates its activation pulse, that pulse begins its exponential decay governed by tau.
Now, when event 2, tear, arrives, the crucial question is how much activation from bit is still hanging around.
If tear arrives while that activation pulse is still substantial within that tau timeframe, the two pulses overlap enough.
And that overlap is the physical mechanism for perceiving them in relation. It creates the emergent group, bitter.
But if the separation exceeds tau, the overlap is lost, the relationship breaks, and they're just perceived as isolated moments in succession.
This is why a 2-second gap breaks the trial linkage in an experiment, and why 1.5 seconds dissolves a melody.
And what's so satisfying is that we have this singular, physical, dynamic, transient activation governed by an exponential decay timescale, tau, that explains every piece of empirical data we just went through.
The phase transition is just the moment the activation pulse from the first event dies out before the second one arrives.
It's a unified and biologically plausible mechanism. And now, having identified this internal constant tau, we have to ask the ultimate question: where does it come from?
Is it universal, or does it vary from person to person?
And this next section is, for me, the most surprising part of this whole deep dive. If tau is this crucial, fundamental internal timescale, it can't be arbitrary. It must be rooted in our biology.
It has to be a function of the body.
Tau equals F of body. And to investigate this, we have to turn to allometry.
Allometry, the study of how properties of animal life scale with body size, usually mass or height.
Right. Allometries are expressed as power laws. For any property you measure lifespan, heart rate, it scales with mass raised to some exponent. Y is proportional to m to the b.
This is how we know larger animals live longer, and smaller animals have faster heart rates. Everything scales.
So the question is, does our subjective experience of time scale with our physical size, just like our heart rate does?
And to measure the scaling of tau, we need a behavioral marker that directly reflects that phase transition, the dragon's edge.
So we go back to the rhythmic pulse.
The watershed tempo. The maximum time between beats a person can maintain before the rhythm is lost to random wandering. That's a direct measure of the phase transition.
So the hypothesis is beautiful and simple. Taller people having larger bodies should have a longer tau,
Their mental activation pulse should decay more slowly.
which means they should be able to maintain a rhythmic pulse at slower tempos than shorter people. They should be able to hold that Gestalt connection over a slightly longer span of time.
So they did the experiment. Gilden and Meserovs measured this watershed tempo in adults and children.
Yes, they had people tap a rhythm and then analyze the time series of their taps, the interbeat intervals.
How did they know when the pulse was lost?
They looked for a specific behavioral shift. When you're holding a rhythm, your taps are tight. But when the tempo gets too slow, you transition from using that internal felt pulse to using your long-term memory. You try to recall the last beat and reproduce it.
And that's when it becomes a random walk. The tempo starts wandering all over the place.
Precisely. They found a very clear point of phase transition into this wandering, and they correlated that temporal watershed with the person's height.
And what did the data show?
A clear allometry. And what was interesting is how they analyzed it. They treated children and adults as two separate groups, but with a common scaling slope.
So the underlying physical rule is the same, even though adults are just bigger and slower overall.
Exactly. They found adults maintained the pulse for about 10 beats per minute slower overall, but the scaling law, the slope, was consistent. And the derived exponent, based on height, was tau is proportional to height to the power of 0.82.
That's a very specific number. But height can be tricky. The gold standard for this stuff is usually fat-free mass, or FFM.
You're right. FFM, your mass minus fat, is a much better biological measure. It represents the active metabolic mass of your body. So they used a formula to translate height and weight into FFM and recast the scaling law.
And the result was?
Tau is proportional to fat-free mass to the power of 0.41.
FFM to the 0.41. That exponent, 0.41, is the first empirical measurement of a fundamental psychological timescale linked directly to the body's size.
It's saying that the decay rate of your internal activation is correlated with your lean body size. And if this theory is correct, that same exponent should show up in other behaviors governed by felt time.
So where else can we look? What's another spontaneous, time-driven behavior that isn't about rhythm?
Speech, our natural speech, pauses.
Okay, how does that work?
The theory suggests that shorter people having a fast rate of activation decay reach what you could call time fullness sooner.
Timefulness. I like that. The subjective feeling that enough time has passed.
Right. And the end of a pause is a choice, a volitional act. It reflects the moment the speaker feels enough subjective pause fullness has occurred. So if shorter people reach that fullness faster because their tau is quicker.
Their pauses should be shorter.
Exactly. And this is testable on massive data sets. They analyzed large studies of unscripted interviews with athletes and celebrities measuring thousands of pauses.
And the finding was clear.
Clear as day. Taller people do, in fact, make significantly longer spontaneous speech pauses.
And did the scaling exponents line up with the rhythm data?
Remarkably well. On the height basis, the exponent for athlete pauses was 0.81, and for celebrities, 0.73. Given all the natural noise in speech, those are statistically indistinguishable from the rhythm exponent of 0.82.
That's powerful convergence. Two totally different behaviors, one a perceptual constraint, the other a volitional expression, are governed by the same underlying temporal constant, tau.
And they scale with size in the same way. This is the moment we solidify the connection. We know tau scales with FFM at an exponent of 0.41. Now, the final critical question.
Does this scaling law converge with any known physiological scaling laws?
We're looking for an internal physiological process that scales with the body at that same exponent of 0.41. What are the candidates?
Well, you could check whole body movement, like walking.
Right. The speed of maximally efficient walking. Your leg acts like a pendulum, and the time it takes to swing is defined by physics.
Longer legs, longer swing period.
Yes. And that crossing time for walking scales as FFM to the power of 0.25.
0.25. That's statistically different from our psychological scaling of 0.41.
It is. So the body's most efficient motor rhythm is not our internal clock.
Okay, so what about the general physiological time scale, like our metabolism, our heart rate?
That's where we look next. If you directly measure the heartbeat period, the time between beats, and plot it against height, you get an exponent of height to the power of 0.79.
0.79 on a height basis. That sounds extremely close to our psychological numbers, 0.81 and 0.73.
And when you perform the crucial last step, when you convert that 0.79 height exponent back into the fat-free mass basis,
What do you get?
you get heartbeat period is proportional to FFM to the power of 0.40.
Wait, hold on. The empirically derived allometric exponent for the mind, for the phase transition of rhythmic pulse, was FFM to the 0.41.
And the physiological scaling law for the heartbeat period is FFM to the 0.40.
That alignment isn't just close. It's virtually identical.
The mind's intrinsic temporal constant and the heart's intrinsic physical constant share the exact same scaling law.
This is the grand synthesis. It suggests this profound physical anchor for our entire temporal experience.
The rhythmic pulse in our mind isn't some abstract cognitive thing. It's physically constrained by the same allometric laws that govern our cardiovascular system.
So the theory holds. Taller people who have a longer heartbeat period, defined by that 0.40 scaling, literally operate on a slightly slower subjective timescale because their activation pulse, their tau, decays more slowly.
Their perceived now is slightly elongated relative to a shorter person's now. It's not a huge difference, but it's measurable and statistically significant.
This just flips the standard cognitive model on its head. We think of the mind as this independent software, but here the hardware, the physical size of the body, is fundamentally dictating the operating speed of our perceptual software.
So we've completed this fascinating journey. We started by challenging sensory psychophysics, replacing that unbounded linear view of time with the Gestalt dragons of a phase transition.
We then relentlessly charted that hard boundary, finding the universal 2 ± 1 second limit confirmed everywhere, in music, in experimental design, in the very choreography of human action.
We traced that limit to a specific dynamic mechanism, the exponential decay of transient mental activation, defined by the timescale tau. The loss of that tau overlap is why events stop forming meaningful groups.
And finally, we anchored that elusive psychological timescale, tau, to the physical body using allometry. And we found that astonishing convergence.
The scaling of our internal rhythmic pulse 0.41 on an FFM basis aligns perfectly with the scaling of our physiological heartbeat period at 0.40.
The profound implication here is that the boundaries of our immediate perceptual reality, the horizon of our subjective now, are not arbitrarily set by culture or cognition.
They are constrained by the same fundamental scaling laws that govern our basal metabolic rate and our heart rate. The physical body dictates the experience of time.
So let's leave you with one final thought based on all this. In studies of time interval discrimination, researchers found something interesting. When people judge intervals longer than about 1.2 seconds, right where felt time starts to fail,
Where the dragon looms.
counting helps them achieve much higher accuracy.
Of course, counting, whether in your head or by tapping a finger, works because it converts a long single interval that exceeds tau into a sequence of short, manageable, rhythmic groups. It subdivides the time into chunks that fit within your capacity of apprehension.
But think about the paradox this creates. We just spent this entire deep dive proving that the rhythmic pulse, the very tool we use to overcome the limits of felt time, is itself anchored to our body's constraints, defined by that same tau.
So, should we rely on the internal subjective feeling of time for those short intervals where it's robust and immediate? Or should we always default to counting subdividing time rhythmically, even though we know that the rhythmic counting strategy is just another manifestation of the very same body size limitations that define our subjective tau?
The tool we use to overcome the limits of our internal clock is itself limited by the physics of who we are. It's this wonderful, complete loop of constraint. Think about that the next time you tap your foot waiting for the train. You're not just counting time. You're actively performing your own unique, physically defined temporal reality.